Swayam Prabha. Digital India. Educated India.
Okay, so in the last class I was talking about Markov chain as a scheme, a method to generate a trajectory of a stochastic process, taking an example of a reactive system. Just to illustrate the idea, we took the very simple model, but in this class I think we will build on it and do more complex reactions and really bring the power of this method. This method is more useful when you have more complicated reaction schemes, which may be very difficult to solve using chemical mass equation. Okay, so we are kind of resorting to a numerical type like solution methodology. So in this class I want to talk about Markov chain, chemical reaction, spatially homogeneous or a batch system, no inlet, no outlet. Maybe in the next class we will talk about CSTR kind of system. To illustrate the idea, I am going to take 4 examples. The first one is a simple irreversible reaction involving only 2 species, but I am bringing a stoichiometric coefficient here. So 1A1 gives 2A2, okay, and the second is the same as first one, but then I am also making it reversible. Then I have a series reaction, okay, A1 giving A2 and then A2 giving A3, and then you have a triangular reaction where A1 gives rise to A2, A2 gives rise to A3 and A3 can give rise to A1, okay, with the respective constants. So what we want to do is take each of these case as an example, construct the transition probability and then write an algorithm for updating the system state with respect to time. So here, like I said before, time is discretized. We are going to use some sort of an integer variable to describe time, okay, m is equal to 0, m is equal to 1, 2, 3 like that, and then the real time will be you have to multiply by some delta t, okay. So then of course you need initial condition, and once you know the transition probability, then we know how to propagate the system, okay. So we will take each example one by one. In the last class I did not mention exactly how we derive the transition probabilities, so here we will discuss more of that. So let's take the first one. So we have A1 giving rise to 2A2 with the rate constant of K1. So here what we have is, suppose if I want to model this as a deterministic process, we would write that R1 is equal to dc1 by d2 dt, right? This is equal to minus k1 c, right, where c1 is the concentration of species 1 and r1 is the rate of the reaction, right? So now if I integrate this equation over a small time delta t, so if I take this equation, okay, I am writing the rate equation for the first species. I got the phenomenological rate equation. So here I am integrating this equation over a small time delta t, and this can be now written as C1 m plus 1 minus C1 m by delta t, where m plus 1 means t plus delta t, m means t, okay, and over this time delta t we have minus k1 c1 t, okay. So now you got an expression that relates c at m plus 1 and c at m, okay. So when you rewrite this, you can relate the next time step concentration using the current concentration with some variable that changes. So this is more like a transition probability for this change. Now this is for only species 1. Now I got another species also. So what I should be able to do, I can repeat the same exercise for species 2 also, okay, and then get a similar expression for C2. So here we write R2 is equal to dC2 by dt is equal to 2 times K1 C1. See, there is a factor of 2 here because when one molecule decays, it actually creates 2 molecules of A2, okay. So that's a stoichiometric coefficient that comes in here. Again, we integrate this equation over small time delta t, so we will get C2 at time t plus delta t, in other words m plus 1 minus C2 at m like this. So you can see that the change in the number of or the concentration of species 1 depends only on the concentration of the same species the previous time, whereas when you look at the change in the concentration of the second species, it depends on itself, it also depends on the other species which is C1. Okay. So now what we can do, we have two independent equations here, we can actually write this equation. Yeah. How do we write this one? Here, this one. So you see that when this forward reaction happens, A1 is decreasing, but A2 is actually increasing, right? So that's why here I have a minus sign to denote the depletion of reactant A. So here I have generation of reactant or the product A2. But this K1C1 is a rate of reaction of A1. But every time one A1 decays, it creates two A2. So this is the stoichiometric coefficient that so now I want to write these two equations in more like a more compact matrix form. So I say that C1 m plus 1, C2 m plus 1, so when we write this in matrix form, this C1 at m plus 1 should be equal to, you take this row vector and multiply with this column, right? So you get C1 m times 1 minus K1 plus T plus 0 times C2. That's what this expression is. Okay. Similarly, if you take this one, you have got both C1m and C2m, both are actually contributing. So for C2m plus 1, you take this row vector and then multiply element wise in this column. So you'll get C1 times 2K1 delta T plus C2 times 1. There is this. Okay. So these two set of equation we are basically writing in this matrix form. So this is concentration at m plus 1 step is related to the concentration at mth step by a transition probability matrix. So here we can think of each of this element as P11, P12, P21 and P2. Okay. Sorry. This is going from 1 to 2. Yeah. What's the problem there? Yeah. So what I'm doing is I have got two linear equations here, right? I'm basically writing into a matrix form. That's all. I'm not doing anything else. So if you operate this multiplication, you will basically get these two equations. Okay. It is only writing it in a different form so that we can say that the next state is related to the current state times the transition probability. And the transition probability, here we have two states, molecule A1, molecule A2, and we have 4 combinations. A1 can remain in A1, that is this probability, or A1 can react to A2 with this probability or the transition probability, or 2 can become 1 or 2 can remain in 2. So here we have an irreversible reaction. A2 can never become A1, right? That's why this probability is 1. And also 2 can never become 1, so the probability of this is actually 0. So you can match the coefficients and identify what is the transition probability between these two states. Any questions here? So in the last class I didn't discuss all these mechanics. I just proposed let the probability be this, and then we operated how it is, how the system evolves. So here we give a mechanistic detail of why we write that equation in terms of the probability, transition probability. Yeah, so when we write in terms of probabilities, we do that, but now I am writing in terms of concentrations and number directly. Because if you remember, I first did with the probability, then I converted into numbers. Numbers need not actually add up to 1. Okay, so here we just keep the directly we write in terms of concentration and number. In fact, here I have written in concentration. You can just replace with number also. Okay, so if you work in a probability terms, then there are some rules we have to follow. I think it is more easy, more direct for this particular approach. Okay, so you can see that what we have done then is we have written, suppose if I write this as a variable c of m plus 1 is related to, so you can write in shorthand notation. This is a state vector comprising 2 of this at m plus 1 step. This is a state vector at m, and this T is the transition matrix. Please ask me if you have any questions here, because this is very starting point, and from here onwards when we go to other cases, things are going to be a little bit more complicated, more terms will come, and so it's important that we understand this elementary example, right? Now, as I said, if you want to work with the number of molecules, you can also write this in terms of number of molecules. This example is chosen such a way that all the elements of the transition probability matrix is independent of the current state. So this system will reach some sort of an equilibrium state where all A1 would have actually completely converted into A2, and that's where system stops. Nothing else happens. We will see some other example where these elements can also depend on the current state of the system, in which the transition probability itself is evolving with respect to as the system evolves. So that depends on the reaction scheme that we are going to discuss. So yeah. Here. Here. Yeah, because we are saying that in this delta t, we are taking so small, any change in this is actually neglected. So we only deal with the derivative term to discretize. So the accuracy of this depends on how small you take delta t. Here. Because this rate depends on the current state. This is a rate. On the left hand side you have a rate, and that rate depends on the current state concentration, not the next. This is more like a propagation, right? So to see the change, what's happening to the next time step, you need the current information. Yeah. There is another method of deriving the transition probabilities by introducing some definition of the transition probability, but I will resist that temptation because I don't want to bring in too many details. Let's stick to this particular framework because this is more intuitive, because we know for a given reaction we know how to write the phenomenological deterministic rate equation, and then all we need to do is this kind of do a discretization over small delta t, rearrange the equations. You will get as many equations as there are number of reactions, right? Number of equations you will get here will depend on the number of reactions you have, so number of species you have, okay. So then you basically write this in this kind of cyclic form or the recursive form, where you start at m is equal to 0 and then update m is equal to 1, 2, 3, 4 all the way, and you will get concentration or the number of molecules as a function of time. That is basically the trajectory of the system, okay. And here we are tracking all the species concentration also, okay. All right, yeah. That's what I was telling her. We are not working on a probability terms now. We are talking about in absolute concentrations and number of molecules, okay. No, it is not. It is basically a transition rate, okay. Okay, now let's go to this particular reaction where I'm going to add a reversible step here with a constant K2. So then when I write the equation here, I will get plus K2 C2 squared. See, the reversible reaction here, I am considering this an elementary reaction. It's a bimolecular reaction. So the rate of the backward reaction is K2 times C2 squared, okay. And then we do the same thing here. The left hand side we integrate, and the right hand side I'm going to have additional term which is K2 C2 squared M. Similarly, for species A2, the rate of change or the rate of reaction is a forward reaction minus the backward reaction. This equation is a simple rearrangement of this. Please check if this is okay. So now I got two equations for two species, and I can write this in terms of the matrix form here. So here you can see now that since we have a reversible reaction, all 4 transition rates are finite. So this is a rate at which molecule A will remain in A, this is a rate at which A will become A2, this is a rate at which A2 will become A1, and this is a rate at which A2 will remain in A2. Okay, and you can see here you got this C2M coming in here, and this is dynamically evolving variable. So the elements of this transition matrix now becomes a function of time through these variables, right? I suggest you try these 2 examples by yourself while I do it in the board and cross check your answers. Okay, if you have understood the idea based on these examples, you should be able to do this also. Okay, so try this yourself. I will also do it in the board for you to cross check your answers. Any questions, by the way? Are we clear here? How are we supposed to solve this numerically? Right? You're going to choose what are the inputs we need. We need K1, we need K2, we need delta T, which you can choose. Then you get this transition matrix at time t equal to 0, because at time t equal to 0 you would also have the initial condition. Initial condition known, initial transition matrix elements are known. With that you update the information for the next time step. Okay, and update the elements of this transition matrix at another time. Okay, and then do this over and over. That's why we call it a Markov chain, because it goes from one state to the other in a discrete way. Okay. Sorry? Yeah, you were saying? Here, this one? Here. This one? Oh, okay. Oh, okay. I see. Yeah, you're right. This should be 2. Uh, 2. Mm, is it okay? Yeah, thanks for pointing it out. Okay. How many of you got it? All of you? Very good. Okay. So now try the other one. Third one. Fourth one. You have to be only very careful about the stoichiometric coefficients. In these cases, the stoichiometric coefficients are just only 1. Whenever there is a other than 1, even the stoichiometric coefficient is other than 1, you have to deal the way that we dealt with the first 2 example. Okay, so that you have to be careful with. Okay, so try the fourth one. If you think this is trivial, make all of them reversible also. the first two examples, there is a asymmetric stoichiometric coefficients. That's why the probability rates were not adding up to 1. But the third and fourth problem, you see one molecule give rise to another molecule. So the number is always conserved. So if you add each row, you will see that for this problem and the one before, you will see it will actually add up to 1. So with the chemical kinetics, you have to be a little bit careful about stoichiometry. Okay, if the stoichiometries are always 1, then you will see this transition rates adding up to 1, confirming the probability expectations. But when there is a non-symmetric stoichiometric coefficients, then this probability won't, the transition rates don't add up to 1. Okay. Okay, so is it correct? How many of you got it? Yeah, good. Okay. So, yeah. Okay, you're not very audible to me, and you're comparing this method with. Yeah. Yeah. So, like I was saying that in the, so this, like I said, this is also kind of a semi-numerical method, which has a deterministic character also. So, actually I changed the framework a little bit. So, you can actually build the entire transition probability, all these models, more from a Markov process itself. Okay. So, right now I thought that is going to be a little bit complicated to understand. So, I am trying to bring in the deterministic kind of way. Okay. So, this actually has a more like a deterministic character, just like how you do a finite difference method of integrating. Okay. So, this method is called Markov chain, right. Markov chain is much broader framework. We are actually kind of customizing that for a chemical reaction kinetics. So, this framework is very similar to deterministics. Okay. But what we are doing here is this when you do this in terms of concentration, you will see this is very similar to the deterministic framework. Suppose when I do this in number of molecules, when the number is finite and small, then you will see that the trajectory is, you will see the stochastic nature of the system. So, this approach can be used for deterministic in the concentration variable, or you can also do it in the number of molecules framework, where you see the stochastic fluctuation more and more clearly. Yeah. Otherwise, it has a lot of deterministic character. And in fact, I thought this is more useful because without any new learning, we can set up the transition probability right from here. Okay, we don't need to learn anything more. Okay, even though there is again a completely probabilistic framework, even to derive the transition probability for reaction kinetics, that takes us slightly away from our scope of the problem. Okay, so you bring in the collision theories and transition rate theories, and from there you build the transition probabilities. I thought maybe that's not the right thing to do at this point of the course. Okay, so we'll use this approach. End of the day, we are going to get the same expression. Okay, and this is more intuitive. Okay, that's a very good question, because I didn't kind of remark that point, that this framework, if you use concentration variable, it's just a deterministic way of solving it, like an Euler method, right? Very simple. On the other hand, if you use the state variable as number of molecules, then you will see that the number, it fluctuates, and then you can get all the stochastic nature of the system. Okay, basically the finite size system effect can be seen. All right. Okay, so that's all I got to say today. And what I want to do next class is that we have looked at batch system, batch reactor, well mixed. I'll probably do 1 or 2 problems in the next class on CSTR, where a species can come in and species can go out, and then how do you integrate that in the equation and again generate its Markov chain. Okay, and then I also uploaded several papers on the modeling approach. How many of you have seen it? Okay, good, some numbers. So I think I put some 25 plus papers just to get enough variety. You will see most of them are deterministic models. There are few models which are stochastic. Okay, so what you could do is you know, and there are a lot of different topics. There are infection dynamics in hospitals, infection dynamics in animal models, infection models for humans, and various antibiotics and so on. So pick up the topic that that you think relevant or interesting, and then read through the paper, understand the deterministic model, and see if you can convert that deterministic model into a Markov chain model or a chemical master equation model, and see if you can benchmark some of the resources. So that's what is expected of. Okay, and I'm also available to come and if you want to come and discuss with me, I'm always there. And choose the paper soon so that you have enough time to work on the project. And as I said, if you want to do on your own, if you want to choose a topic other than that, that's also fine. But you have to tell me what you're going to do. All right.